Hi, this is Lakshmi Kantiwari. In this lesson, I'm going to teach you principal component analysis with the Python. Okay, so in a principal component analysis, we will first go with the introduction of the principal component analysis, and then we will learn how it works, and then finally when to use a PCA. Okay, and then finally with the visualization with a very good GIF, we will understand actually how these the PCA works, and then after that we will see the summary of principal component analysis in these 7 steps. Although I'll not take you through a deep mathematics, but for beginners it will be good to understand overall the pseudo algorithms of the principal component analysis. And then I'll be analyzing the breast cancer data set, okay, where we will be compressing the 30 dimensions into lower dimensions, around 5 to 8 dimensions. Okay, so we'll be using here sklearn in a Python, and then finally we will be visualizing this data set where you can see it's kind of linearly separable if we reduce it into a 2 dimension. And after that we will see how the variance of in PCA is decreasing. Variance is decreasing when we are increasing the principal components, I mean the dimensions of your data. So the moreover with this graph you will understand that if we increase the number of features or the dimension in the data, it is not always necessary it will increase the performance of your model. Okay, and then finally we will learn what is the advantage of a principal components. And apart from that, I have been teaching machine learning previously. If you haven't watched my previous videos, you can go ahead at my channel KGP Talkie. There I have uploaded many the videos on the machine learning, and if you want all these videos at a single place, then go ahead in the playlist machine learning with theory and examples in the Python. There I have placed all my previous machine learning videos at a single place. Okay, perfect. Now let's go ahead and learn a principal component analysis without wasting a time. Principal component analysis is a linear dimensionality reduction technique that can be utilized for extracting information from a high dimensional space by projecting it into a lower dimensional subspace. So here I have an example for a PCA explanation. Let's suppose that you have a very high dimensional data and you want to reduce it into a lower dimension. For example, here in this example it is reduced into just a 2 dimension. So the first dimension where it has the maximum information is known as a first principal components, and the second highest the component which has the second highest information is known as a second components, and so on. So how it works, it tries to preserve the essential parts that have a more variation of the data and remove the non-essential part with a fewer variation. So the question comes, what is the dimension? Dimension are nothing but features that represents the data. Okay, for example, if you consider a 28 cross 28 MNIST data set, so if we multiply 28 into 28, then it becomes 784 the picture elements are the pixels. So that's the huge dimension. But with the principal component analysis, we can reduce that a huge dimension into a lower set of the dimension. Okay, let's say for example in just a 2, 3 or 4 dimensions. Okay, according to the Wikipedia, PCA is a statistical procedure that uses an orthogonal transformation to convert a set of observation of possibly correlated variables into a set of values of linearly uncorrelated values, those called the principal components. So if I say here uncorrelated variables, that means those variables are orthogonal to each other, our vectors are orthogonal to each other. If I say that the 2 vectors are orthogonal to each other, that means they have a 0 correlation between them. So this is how principal component analysis works. It converts non-orthogonal the features or a space into orthogonal space by reducing its dimensionality. So the one important things to note about the PCA is that it is unsupervised dimensionality reduction techniques. That's when there is no final level where we can match and we can get accuracy or confusion metrics. So you can cluster the similar data points based on the feature correlation between them without any supervisions. Okay, so you will learn how to achieve this practically using Python and the sklearn library in this tutorial later on. But for the introductions, this is how the principal component analysis works. But the question comes when to use this principal component analysis. So there are two things where you want to use: for a data visualization and speeding a machine learning algorithm. Why data visualization? Let's suppose that you have a huge dimensional data, as we had seen in 28 cross 28 MNIST data set where it has more than 700 dimensions. But suppose that when you are not able to see the data in the multiple dimensions. With our naked eye we can see the data in just 3 dimensions, but for more than 3 dimensions it's difficult to visualize it. So if the data is more than spread in more than 3 dimensions, then with the PCA, principal component analysis, we can reduce the data in 2 or the 3 dimensions to understand what is the data. And for the speeding the machine learning algorithm, how it will speed up the machine learning algorithm? Let's say if the number of features or the dimension of the data is high, then of course the training and the testing time will be the high. But with the PCA, if we decrease the dimension of the data, then it takes less time to train and test your machine learning algorithm. So ultimate, as a result, it speeds your machine learning algorithm, as well as space complexity is also saved. That's mean it takes less space to save your overall the data on your hard disk or a computer or a cloud, anywhere you are saving it. Now the question is how to do the PCA. Okay, as there are many principal components, as there are variables in the data. That's mean, let's suppose that if 10 features are present in your data, then there could be maximum 10 principal components. Okay, so the principal components will be the always lower than your total number of features present in your data. Okay, so the principal components are constructed in such a manner that the principal components accounts for the largest possible variation in the data set. For example, in this plot you can see here, and this data is spread into, let's say, the 2 dimension, and here is the principal components, it varies. Okay, so if you see here, if it matches here, then you see the dispersion of these data points are the maximum. Okay, so that's the variation maximum, and in this way you see the variation is the minimum. Okay, that's when these data points were highly densitized at the same place, but here if you see at this point the variation is too high. So in this way we can say that this is the principal components, the first principal components, and when it aligned with this the magenta line, then you see here it's perpendicular, there is another line. So this is the second principal components. Okay, so this is how we calculate the first and the second or the third principal components, and so on. Okay, now the question is how it do behind the scene all these principal components, etc. things. Okay, so in a nutshell, if I say to you how it do all these things, okay, so there are a few steps. So I'm going to explain you in just 7 steps, a simple 7 steps. In the first step, let's say you have these uncorrelated, the correlated high dimensional data. If I say the correlated, that means it's not highly correlated, but somehow it is correlated, or it could be highly correlated, who knows. Okay, so the first we start calculating with the center of the points, and then we calculate the variance of these data. Okay, so how we calculate the covariance matrix, and with these covariance matrix we calculate the eigenvectors and the eigenvalues. Okay, and once we calculate the eigenvectors and the eigenvalues, then we pick the m such that the eigenvectors the reduced, And once we get the reduced eigenvectors there, then we project this data into those eigenvectors, okay, in those reduced eigenvectors. And once we project those data in those eigenvectors, then we do the inverse transform and we get an uncorrelated low dimensional data. Moreover, mathematically this is a little bit the complex, but you can understand that in mathematics we compute covariance matrix, then we calculate the eigenvectors and the eigenvalues, and based on those eigenvectors and the eigenvalues we do a reduction of the dimensionality. But luckily in a Python, scikit library has done these tasks, has reduced the overhead for us. So in a scikit-learn library we have a PCA. Their principal component analysis, the package in scikit-learn, we just call the PCA, and then finally we call a fit, okay, as usual we do in a machine learning other algorithms. And after the fit, it do the all the principal component analysis and the dimensionality reduction. And that fit transformation that takes an input, which actually input, that's mean that input is how many dimensions we want in a PCA. Okay, instead of just going with the theory, let's go ahead with an example, then you will understand exactly how you can code your principal component analysis algorithm in a Python. So in this lesson we will be working with the breast cancer dataset. But before loading a breast cancer dataset, let's go ahead and load other essential libraries in my Jupyter notebook. So first of all, we need to load the pandas. So you can type here import pandas as pd, and then import numpy as np, and then I need to import seaborn as SNS, and then I need to import matplotlib.pyplot as plt. Okay, apart from that, let's go ahead and import dataset metrics and trend test split from sklearn library. Then here we need from sklearn import datasets and then metrics, and then from sklearn dot model selection import trend test split. Okay, perfect. Now let's go ahead and load our breast cancer dataset. There we have datasets dot load breast cancer. Once we load this dataset, now let's go ahead and get a description of this dataset, which we can get with the print.cancer.descript. Okay, in this we get here the description of this dataset. There you see total 569 instances, or you can say this number of rows, and it has 30 dimensions of the data. Okay, and it has 30 dimensions, that's mean 30 features of in this data 30 features are present, and the set of the features are these. Okay, so these are the set of the features, there is no missing values, and we have two class. There are two class, whether the cancer is the malignant or benign. Okay, so if cancer is the malignant, that's mean it's the serious one. But if cancer is just benign, then there is no harm, it's not a harmful cancer. Okay, perfect. Or the tumor, whatever you say. Of course the cancer is always harmful, but it's if it is a tumor, if it's a benign tumor, then it's not a harmful. But if it is the malignant, then it's, of course this is the harmful, and it could be a cancerous tumor. Now let's go ahead and visualize our the data set. First this data set, how we can do that. Let's load it into first pandas data frame with the df is equal to the pd dot data frame, and there we have a cancer dot data. So this is the data where we have our actual data, those 30-dimensional data. And then if we say the columns is equal to cancer dot feature name. So here those feature names are given. Then if we visualize, if we see this with the data frame head, then you will see here all those 30 are the 30 features. And apart from that, these are the first 5 rows in your data set. Now let's go ahead and one more thing, you can see here the dimension of the each features are different. The scale of each features are different. Okay, this is quite in the tens number. Okay, 17, 20, and these are the less than 1 mean smoothness, but mean perimeter is around 100 and are more than 100, and the mean area is more than thousands or somewhere. So it's kind of not in the same scale. So it's always advisable, if you are working with the machine learning algorithms, then always standardize or normalize your data before applying any machine learning algorithm. So let's go ahead and standardize this data with a standard scalar. Then we need to first import standard scalar from a scalar. So here we can say from from a scalar dot pre-processing import standard scalar, and now we need to put here the scalar is equal to the standard scalar, and then now we have s scaled version of x, and that's the scalar dot fit underscore transform of x. Okay, now you will see here, I think before that I have to get the x and that x I can otherwise I already have df actually, so we don't need x. So let's go ahead with the df there. Now if I visualize here x is scaled, then you will see here all the data, all the columns of these data has came into a -3 to +3. Generally, if we standardize our data, then we get somewhere our data -3 to +3. Okay, so now let's go ahead and import the PCA from a scalar library. From a scalar dot decomposition import PCA. Perfect. Now here we have a PCA is equal to PCA, and then here we have n components. Number of components we are going to just take a 3, and random state I'm gonna put a random state so that we can get the same result as I am getting. That's meaning you can get the same result if you use a same random state. PCA dot fit x underscore scaled. So now you see here it has trained the model. Now we need to just transform our data into 2 dimension. So here training has been done in this step. Now let's go ahead and transform it with now here I'm gonna write here x underscore PCA is equal to PCA dot transform. Now we need just x scaled data. Okay, now you see here our data has been transformed. To check this, what I can do, I can check the shape of x scaled as well as I can check a shape of the PCA x PCA. Okay, sorry. Now you see here the shape of the default data is 30, but after transformation the scale of the data has become a 2. Okay, perfect. Now let's go ahead and visualize this into 2 dimension of the data. Okay, in the 2 dimension, this is scaled, this decomposed data. Okay, so this is the reduced dimension. What we can do, we can visualize this using matplotlib library, but we need to first initialize plt.figure so that we can set a figure size. I'm gonna set here 12x8 figure size, and then plt dot I'm gonna do here a scatter plot. Okay, so if you see here XPCA, in XPCA here I'm gonna get a first column. Okay, and then that's the X is the first column, and here I'm gonna get here the second column as a Y. I'm gonna pass here, and I'm going to also pass the color scheme that would be related to the target. That's mean whether the cancer tumor is malignant or benign. Okay, so there I can pass from the cancer dot target. Okay, and the CMAP, the color mapping, I'm gonna use the VDDS. Okay, perfect. Now let's go ahead and see this. Now if you see it something like this, but before that I'm gonna also give here the X and the Y label so that you can understand which one is the first principal or principal, the first principal components, and which one is the second principal components. Okay, first principal component plt dot y label, that's the second principal component. Now you see here, so this X is the first component and the Y axis is a second principal component. Okay, perfect. Now one more thing here. The thing is that I have been talking a lot about the components, but do you know how it works? Okay, so the working principle I have already explained you, but you know it has a magnitude and the direction. So every principal components have a magnitude and the direction. The direction represents across which principal axis, and the data is mostly spread out and has a most variance. That's mean if you see, which I had explained here, the eigenvectors directions, okay, the projections which you can say. So these projections, these eigenvectors projects in the directions where the maximum variance presents in your data. Okay, and the principal components are a straight line, and the first principal components holds most of the data. These first principal components holds most of the data, and the second principal components holds most of the data, but after the first the principal component. That's when you can say each subsequent principal component is orthogonal to the last and has a lesser variance. So in this way, given a set of the X correlated variable over Y samples, you achieve a set of let's say the Z uncorrelated principal components over the same Y components. Okay, so here in last, what we can say here, the each principal, these components, okay, represents some percentage of the variation present in the data. Now I have been talking a lot about the variation present in the data. Do you know we can get those variation amount according to the principal components? So this is the flexibility what sklearn provides us. Okay, so here I am going to show you how you can get the more information about the PCA. You need to just write here the help and then PCA. Once you write here help and the PCA, you will get here a detailed information about principal component analysis, which is the kind of the documentation present into a sklearn package. Okay, so it says that the principal components, it's a linear dimensionality reduction using a singular value decomposition, which is known as SVD. Okay, SVD works on the principle of the eigenvectors and the eigenvalues. Okay, so here are the input parameter which it takes, like n components, the copy, whiten, SVD solvers, etc. and etc. And these are the output attributes which it returns, like the components, explained variance, the variance ratio, a singular value, etc. and etc. Okay, so let's go ahead and see the variance ratio which we are getting, okay, in our in case of our data. Okay, so we can type here the PCA dot explained variance ratio. Now you see here the first principal component have a maximum variance, which supports our statement which I said while describing this image. Okay, perfect. Now let's go ahead and see if we plot this in 3, 4 or 5 principal components. So let's represent this data in 3, 4 and 5 principal component and see how this variance ratio decreases or increases, whatever happens. Moreover, fundamentally it will decrease and it will always decrease. But if dimension increases more than the 3, it would not be possible to visualize those data easily. So if I go ahead with the more than the 3 principal components, then I would not be able to show you this plot, but we would be able to see the variance, okay, which we have been talking about here earlier, the variance or spreadness of this data. Okay, perfect. Now let's go ahead and plot this using the matplotlib. So first of all, that we need to get here the principal component analysis. Okay, so let's go ahead and get a PCA for the 8 dimension. Okay, so here we have 30 dimensions total, but here I'm gonna just take the 8 dimension. So let's go ahead and take here the PCA, and then I'm gonna pass here n components. N components is 8, and random state which I'm gonna pass here just 42, and then PCA. Let's get x underscore PCA directly from PCA underscore fit transform. So it will automatically do the training and transformation in a single line of code. Then here we have our DF, that's the data frame. Okay, and then here we have let's say the variance is equal to the PCA dot PCA, sorry, yes, so this should be the PCA dot the explained variance underscore the ratio. This says that the PCA object has okay, perfect. So here we have got variance, and if we visualize this variance, you will see here the variance ratio. So moreover, I am going to plot this into a bar plot. Okay, so that can be done just a plt dot bar plot, and then x data I'm gonna pass here range. So that's mean the x-axis. So x-axis is going to be spreaded from the first principal components to the length of this variance plus 1. Okay, that's mean total 9, total 8, sorry. And then we need to pass here the height. Height is actual data, that's the variance. And let's go ahead and write here with 0.8 or 0.7. Now let's go ahead and plot this. Okay, once we plot this, you will see here the most of the data it is being fit at the first place itself, but after that the variance is decreasing. Now let's go ahead and decrease this to the 5. Now you will see here, okay, this is how it is becoming. And if we decrease it to the 2, now you will see here something like this. Okay, perfect. One more thing I think we are missing here somewhere. Okay, we need to pass here actually x is scaled. That's why it is not matching, the earlier. We need to, that's mean, the scaled version of the data, right? So here now you see the first principal component was around 0.46, and here the second one was around 0.18. Now let's go ahead and visualize this for 8 principal component analysis, right? See here how the information is decreasing as we are increasing the number of components. Let's go ahead and make it the 20. Now you will see here after 5 or the 6 or 7 principal components, 5-6 principal components, the further the data, I mean if we are increasing the dimensionality of the data, it's not improving our data set. It's not improving actually the variance. Moreover, it will not improve the accuracy as well in most of the cases. Okay, so the overall, this is how the principal component analysis works. Okay, moreover, while these conversions are being done, the principal components, let's say the first principal components, it calculates some kind of the linear relationship between the original feature sets or original dimensions. So this is how these conversions works. Okay, so the organizing information in the principal components this way allows the reduced dimensionality without losing much information, and this could be great for information comparison. Okay, now the question comes, what is the advantage or when to use these PCA? Let's suppose that if you want to speed up your machine learning algorithm, then definitely you can use a PCA to reduce the dimension. Moreover, if you want to decrease the model complexity, then of course you can use a PCA. And it is unsupervised learning and good to use where we want to compress information, and it reduces the space requirements for our data. Okay, where we are saving our data whether on the local machine or on the cloud. So this is all about in a principal component analysis tutorial, and in the next lesson I'll be talking about ensemble learnings in the Python. So thank you so much for watching this video. Please do not forget to subscribe this channel, and if you like this video, if it helps to you, please like this video. Bye bye, have a nice day.